Oh, hey, I didn't see you there. You're watching Crashing with Manny. In today's episode, I'm going to be talking about electric machines. So we have an AC generator, DC motor, and AC motor. In today's episode specifically, I'm going to be talking about a DC motor. So here we have the simplest of DC motors, which you can find in common household items. So here we have the stator, which basically provides a magnetic field, so it acts as a magnet. And then we have the armature right here. The armature is connected to a DC power supply, so say a battery. With this DC voltage, current starts to flow through the coil. And then an electromagnetic force is induced on the coil, according to Lorentz law. Lorentz law states that force is equal to the charged particle Q with velocity v, that it's going through the magnetic field and the electric field. So for a DC motor, our QE, our electric field, are the charged particles that are flowing in the coil this way, in this direction, around the coil. And our QB, B times B, is the direction of the magnetic field. So it's essentially going this way. So you can't really see it, but essentially it's creating a normal vector, so it's perpendicular. So if I were to draw it how it's supposed to look, it would be like something similar to this. And then, which basically is what makes the coil turn. The problem with this DC motor is that there's only one coil. So say we have a windmill with two turbines, and say it was a guy's job to push the turbines around in order to produce power. So as the guy pushes it from the bottom, the momentum is going to slow down as it continues to go around. So like say he pushes it, it's going to go fast, then slow, then push again fast, and slow. So the easy fix is just to add another turbine. So say we have 4 now, then he can easily just push and push and push, and then it'll rotate at a more constant speed. The same thing applies to a DC motor. When the electric coil here, or the coil here, is turning, the second it's perpendicular to the magnetic field, the torque almost becomes 0. So essentially it's doing this. It's behaving like this. Slow, then fast, and as it reaches 90 degrees, slow, then fast, and slow, and fast, and slow. So the easy fix is just to add more coils, therefore we're going to get more rotation, and we'll never have to reach that torque of 0, since it's always going to be rotating. There's always going to be a coil rotating in its place. Oftentimes, a DC motor contains an electromagnet, which contains a field coil or field winding, which is powered by the same DC motor. The field coil or windings are connected to the armature. There are 2 ways we can connect the field coils to the armature. We can connect them in parallel, or we can connect them in series. In parallel, we can create a shunt motor, and in series we can create a series motor. So with a series motor we have our battery, and we have our field winding, then we have our armature. So with a series motor it has good starting torque, however if we were to put a load across the armature, the speed will reduce drastically. With a shunt motor, you have the armature here with the winding in parallel. Now with a shunt motor, the torque is usually slower, however, the speed will remain constant regardless of if there's a load or not. You're watching Crashing with Manny. Catch you next time.